Hello and welcome to the first of the APECE Chapter 17 Spontaneity of Reaction Problem Set Screencasts. This is Mr. Wilkosz. We're checking out problem number 1. In problem number 1, you're asked to decide which processes are spontaneous, and you have to think about, do they happen on their own? So building a sandcastle, you never just walk up across one on the beach unless someone has already built it before. It's not a spontaneous process. Outlining your chem notes? Certainly not. That takes a lot of effort. And wind scattering leaves? That is a spontaneous process. It'll happen without an outside force, outside impact. Question 5. In question 5, you're asked to consider which processes are spontaneous based on your observations and reactions that you should be somewhat familiar with. So zinc with an acid giving zinc ions and hydrogen gas bubbles. That is a process that's spontaneous. The second one, calcium carbonate with water becoming calcium hydroxide and hydrogen carbonate. Not spontaneous. The third one, methane combusting, spontaneous. The fourth one, silver and chloride ions combining to create silver chloride solid, spontaneous. Take a look at problem 9. In problem 9, you're asked to predict the sign of the change in entropy. Delta S is the change in entropy. Now remember, entropy is a measure of disorder. So things that get less organized are actually getting higher entropy, greater entropy. So when ice cream melts, that should be a positive entropic change. You're getting less order, more disorder. Boiling water, getting more disorder, going from a liquid state to a gaseous state. Dissolving instant coffee in hot water, more disorder. And sugar, decomposing to carbon and steam is a more entropic process. These are all things that create greater entropy than what you began with. Let's take a look at the next problem. Problem 15. You're asked here to predict the order of the reactions in terms of increasing entropy. So the things you want to pay attention to like qualitatively assess entropy, not like with a specific numerical value in joules per Kelvin, is the states of matter that are present on each side of the reaction. So you're comparing products back to reactants, and you're seeing how the transition from reactants to products changes the states of matter. So in the first reaction, you're going from two gaseous things to a solid thing. That's getting more organized. In the second thing, you're going from a gaseous thing to a liquid, more organized. And the third thing, you're going from 2 moles of a gas to 3 moles of a gas, so that's getting less organized. And in the third one, you're going from 2 moles of a gas to 2 moles of a gas, so there's not really a significant change in entropy. So you can actually characterize these things in terms of order based on the assessments we just made there, as C having the greatest disorder, D having the next greatest disorder, B having the next greatest disorder, and A having the least disorder through the process. Let's take a look at problem 19. In problem 19, you're asked to calculate the standard entropy change. Now, standard entropy change is measured in joules per mole per Kelvin, and it's measured at 1 atmosphere of pressure for gaseous things, and the ions that are aqueous are assumed to be in a concentration of 1 molar. This is essentially a bookkeeping thing. All of these values that will be reported on table 17.1 on page 456 are reported for 1 mole of them. So if you have more than 1 mole, you need to have a coefficient of 2 run through your specific substance. So in each one of these, you're always going to do products minus the reactants. So if you look at this first reaction, 2 chloride ions plus iodine solid gives chlorine gas and 2 iodine ions. You're going to see that you put your products first, the chlorine, the entropy of the chlorine, plus 2 times the entropy of the iodine, and then minus the reactants, 2 times the entropy of the chloride ions plus 1 of the entropy of the iodine. And all of these values are present on the table again on page 456, table 17.1, and then it's just bookkeeping, summing up, running your coefficients through. The same is true for part B and also for part C. So end answers for part A, you should get a final change in entropy of 216.5 joules per Kelvin. In part B, for the reaction that's listed there, you should get a entropy change of 242.8 joules per Kelvin, and for part C, you get a negative entropy change. It's 43.4 joules per Kelvin.